In this lesson, we will be working on predicting products for synthesis, decomposition, and combustion reactions. We'll start with synthesis. If you remember, during a synthesis reaction, only one product is produced. You have two or more different reactants to start with. So if we take a metal that we're going to represent with M and react it with a halogen, that's group 7A, which we're going to represent with an X, we can make an ionic or covalent compound, so usually an ionic compound. Fluorine is the most reactive halogen and reacts with almost all metals. So here we have sodium from group 1A, that's our metal M, and chlorine, our halogen, from group 7A, that's going to be our X. It's a metal-nonmetal combination, and so we can combine them together into an ionic compound based on the charges. Sodium has a +1 charge, and chlorine has a -1 charge, so that gives us NaCl. Most ionic compounds, if you remember, are solids, so we have that labeled with a little s. And the last step is always to balance the chemical equation. Chlorine here, remember, is diatomic, so that is why it's represented as Cl2, and that's why we need some additional coefficients to balance out the chemical equation. Here we have a group 2A metal, magnesium, combined again with a halogen, fluorine. Fluorine is also diatomic, so that's why it's written as F2. Magnesium is a metal, fluorine is a nonmetal, so we're going to make an ionic compound. Magnesium has a +2 charge, and fluorine has a -1 charge. So MgF2 is our product, a single product for synthesis, and most ionic compounds are solids, so we give it a little s. No additional coefficients are required here to balance this chemical equation. We can also do synthesis reactions with oxygen or sulfur. So an element reacts with oxygen or sulfur to produce an oxide or a sulfide, and almost all metals will react with oxygen. So here we have a group 1A metal, sodium, combined with oxygen, although you could also combine it with sulfur. We get Na2O as our product. Again, we're doing a metal-nonmetal combination. Sodium's a +1 and oxygen's a -2, so we get Na2O. It's an ionic compound, so we label it as a solid. And then we do need some additional coefficients to balance out this chemical equation, shown here. Oxygen, again, is one of those diatomic elements, and so you'll see that written as O2. Here we have a group 2A metal with oxygen, although it could also be with sulfur. Magnesium is a metal with a +2 charge, and oxygen is a nonmetal with a -2 charge. And so we write that formula for that product as MgO. We want the simplest ratio possible. It's an empirical formula. And then we do need additional coefficients to balance out that chemical equation, because oxygen, again, is diatomic. So far, we've taken all elements, a metal and a nonmetal combination, to combine them together to make an ionic compound, a single ionic compound, in our synthesis reactions. We can also do some synthesis reactions with transition metals. Remember, many transition metals have more than one possible charge, and so you could get more than one possible product. So iron typically has a +2 or a +3 charge as an ion. So when combined with oxygen, which again is diatomic, we get a couple of possibilities. Iron with a +2 charge and oxygen with a -2 charge gives us FeO as an empirical formula, again labeled as a solid. And then iron with a +3 charge and oxygen still with a -2 charge gives us Fe2O3, again labeled as a solid, as most ionic compounds are solids at room temperature. And so these equations are also balanced to have the same number of each type of atom on both sides. Nonmetals can also be combined together to make covalent compounds or molecular compounds. These are harder to predict, so we'll stick with the ionic ones. When we do the metal-nonmetal combination, it's easier to predict what the formula is based on the charges. But here are two examples of nonmetal combinations to form some molecules. Carbon and oxygen make carbon dioxide, and hydrogen and oxygen make water. There's one special kind of synthesis that I want you to know, where we take and we combine together two smaller compounds to make a larger compound. This is where we take a metal oxide, like calcium oxide, and react it with water. So we're going to take our ionic compound, our metal oxide, that will be a solid, water will be a liquid, and then we're going to make a metal hydroxide, shown here. This is calcium hydroxide. We're going to label those as solids. So you just have to know this. This is what happens when you take a metal oxide and react it with water. You get a metal hydroxide. You'll have to write the correct formula for the metal hydroxide based on the charges. So our metal here was calcium. That's a +2 charge. Hydroxide is always a -1 charge. Now for decomposition. Decomposition is kind of the opposite of synthesis, right? Where we start with one reactant and we break it into multiple products. Most decomposition reactions are going to require energy, so you will often see that shown in the equation. So we can take some binary compounds and break them into their elements, like we see here with some mercury oxide. We've got this little triangle up above the arrow, which means we need to heat our reaction, provide some energy to get this compound to decompose. We're just going to break the mercury oxide into its elements, some mercury and some oxygen. Oxygen, remember, is diatomic, so we're going to write that as O2, and oxygen typically exists as a gas. Mercury is one of the few elements on the periodic table that's a liquid at room temperature, so a little L there for liquid. And then provide additional coefficients to balance out that chemical equation. Some other special decompositions that we're going to focus on. The decomposition of metal carbonates. So a metal combined with carbonate, like calcium carbonate here, we are going to decompose that, and it always decomposes into a metal oxide, calcium oxide in this case, and carbon dioxide, CO2. So it's kind of like we have to take and distribute the oxygens to get our metal oxide and our carbon dioxide. Of course, we want to write the correct formula for the metal oxide. Calcium's a +2 and oxygen is a -1. And then we write that as CaO as an empirical formula. It's an ionic compound. We're going to write it as a solid. And then carbon dioxide typically exists as a gas. Notice how we have heated this reaction in order to get this calcium carbonate to decompose. So you should know that anytime you have a metal carbonate, you get a metal oxide and carbon dioxide. And then we don't need any additional coefficients to balance out this particular chemical equation. All right, another special kind of decomposition that you need to know, the decomposition of a metal hydroxide. Now, this is the opposite of the synthesis reaction that we just looked at. In the synthesis reaction, we took a metal oxide and water and made a metal hydroxide. So here we're taking a metal hydroxide, in this case calcium hydroxide. We're going to heat it. We get a metal oxide, calcium oxide, and water. And because we're heating this, typically we're going to see that as water vapor. But if you put a liquid there, I'd be okay with that. Again, we want proper formulas for our metal oxide. Calcium's a +2 and oxygen is a -2. This particular equation does not require any additional coefficients to be balanced. The last special kind of decomposition that you need to know is the decomposition of a metal chlorate. Here our metal chlorate is potassium chlorate. And chlorates will decompose into a metal chloride and oxygen gas. So it's kind of like we take and split this compound. We of course want the correct chemical formula for our metal chloride, and so potassium is a +1 and chlorine is a -1, so that's why that's KCl. And then remember, oxygen is diatomic and would be represented as O2 as a gas. Okay, and then we've got an ionic compound here in our metal chloride, so we'll label that as a solid. Again, notice how this is heated to make it decompose. And we do need some additional coefficients to balance out this chemical equation shown here. Finally, our third type of reaction that we're going to predict products for in this video is combustion. In a combustion reaction, we always have a hydrocarbon, so something made of hydrogen and carbon. There could be some other elements in there like oxygen, but the hydrocarbon is going to react with oxygen, and products are always carbon dioxide gas and water vapor. Combustion reactions are always exothermic, so if you want to say that heat is like a product here, you certainly can. But all you need to do is be able to look at the reactants, pick out the hydrocarbon and the oxygen, and then you know automatically what the products are for the combustion reaction. This one did require some additional coefficients to balance out the chemical equation. So now hopefully you know how to predict products for synthesis, decomposition, and combustion reactions.